Okay, so this lecture will discuss in more detail the interactions of particles via the fundamental forces. So what have we learned so far? We learned about the quark model to describe hadrons, and the quarks make up the top two rows here on the left, the up and down quark, for example, but there's charm and strange in top and bottom. Then there are the leptons, which don't interact via the strong nuclear force, which includes the charged versions, the electron, the muon, and the tau. They're neutral cousins, the electron neutrino, muon neutrino, and tau neutrino. But then there are the forces. The electromagnetic force we've discussed can be quantized into photons, right? That was the photoelectric effect telling us that. But likewise, the strong nuclear force can be quantized into so-called gluons, and the weak nuclear force by the so-called W and Z bosons. And for consistency, there's another particle called the Higgs boson, which I'll say a little bit more about in the next couple slides, that makes the whole picture consistent. But we have sort of matter particles, those that comprise, for example, atoms. Up and down make neutrons and protons, add electrons, and you have atoms. And you have particles that describe the forces. Now, what can we say about the theories that comprise the so-called standard model of particle physics? This is not a course, and don't worry that we're going to go into all these details. But it turns out that if we dug into relativistic quantum mechanics, there is a theory for the electromagnetic and weak nuclear interactions, and they've been unified by Steve Weinberg and Abdus Salam in particular into the so-called Weinberg-Salam model, which has a certain group structure, SU2 cross U1. That doesn't matter here. But it actually describes both electrodynamics, quantum electrodynamics, that is, so QED, and the weak interactions. So it's responsible for electricity, magnetism, and radioactive decay. And we have a theory for that. The couplings in that theory are via the electric charge of particles, but also for the weak force, there is so-called weak hypercharge and weak isospin. And to describe this combined unified force, we need four bosons, that is four particles that have integer spin. For the electromagnetic part, you're familiar with the photon, right? But the weak nuclear force has another neutral particle called the Z boson, as well as charged bosons, a W plus and a W minus. So that's the electroweak theory. There's also the strong force, which has a separate theory, which is known as quantum chromodynamics, QCD, and has a certain group structure, SU3. And it's basically describing how quarks bind into protons and neutrons, and also how the nucleons themselves bind inside the nucleus. And the coupling in this theory is via essentially a strong charge, not an electric charge. So we'll say strong charge, but it actually comes into three types, which are known as colors, three colors. Electric charge, you can think of, comes in plus, and then it's anti-charge, which is minus. So like the electron is minus E, and its antiparticle is plus E. So there's only one type of charge, right? The minus for the electron. But the strong force comes in three types. We can call them colors. That's what's actually done in the field, hence the chromodynamics in the theory name. But you could think of it as red, green, and blue as the charges, and you have anti-charges. So you would have anti-green, anti-red, anti-blue, or cyan, magenta, yellow if we're going to do some color theory. And instead of one photon that comprises this force when it's been quantized, if you like, there are 8 bosons known as 8 gluons. And collectively, these two theories, the Weinberg-Salam electroweak theory and the quantum chromodynamics theory, they comprise what I've been referring to as the standard model. Now, all the masses in these models, all those particles would have a mass of 0, unless we introduce a new scalar field, essentially in the universe, a field that has no spin. And that's necessary to allow that the bosons that propagate the weak force to have mass, and they actually have a lot of mass, 80 GeV and 91 GeV for the W bosons and the Z boson respectively. So we need this scalar field, And it's also, we need a scalar field to give mass to the fermions, that is the leptons and the quarks, because they have mass too. And that theory that allows you to do that, called the Higgs mechanism, also has as a outcome a new massive scalar particle that is called the Higgs boson. That little happy guy there on the right, right? Okay, so that's just kind of describing that there are some theories behind the scenes here to describe particle interactions. What we'll do in this rest of the lecture is kind of show graphically how to draw what's happening and what's taking place in these interactions, although not exactly calculating quantitatively the results. So, interactions. So as I've been saying, the fields associated with the fundamental forces are conveyed via particles. And this is known as second quantization in relativistic quantum mechanics, or perhaps now referred to as quantum field theory. So the forces themselves have been quantized, if you like, into particles, like the photon. And indeed, for electromagnetism, it is the photon that propagates that force in this relativistic quantum theory. And we'll use the Greek letter gamma to denote it. And if we're going to draw a graphical representation of a scattering, we typically show a little wavy line. That's kind of to illustrate the wave-like nature, right? Electromagnetic waves. And we'll put the gamma there to label that. The weak force can be propagated by three different types of bosons. The Z boson, which is electrically neutral, and the W plus or the W minus bosons, which are electrically charged. We'll also draw them with a wavy line because, hey, it's been unified with the electromagnetic force. But we can also write the type of boson above it there, like a W or a Z. Then there are the gluons, which propagate the strong nuclear force. And we're going to write a G for gluon. Makes sense, right? And well, gluons hold things together like the nucleus. So we can kind of think of them as like springs. So we'll draw kind of a springy thing here with a G above it for denoting the gluons. Well, in gravity, well, what about gravity? If it were quantized in a relativistic quantum mechanics theory, we would call these particles gravitons. But unfortunately, we don't have such a quantum theory yet for gravity. The jury's still out. Maybe one of you will help figure this out in the future. All right. To describe how interactions take place, we're going to borrow a technique that dates from Richard Feynman, where the interactions between particles can be denoted by space-time diagrams, which you may remember, it's a bit like what we've done in relativity. So we can draw, say, a spatial axis along one direction and time along another axis. So let's say we're talking about the scattering of two electrons. We have electron above and electron below, which are going to approach each other in space, but they're going to repel, right? They're going to scatter. They feel a force. And how does that happen quantum mechanically? They exchange a particle. They exchange one of these photons that makes up the electromagnetic force, and that causes the electrons then to scatter. And we have a whole theory, quantum electrodynamics, on how to calculate the rate for that to happen based on the coupling of the photon to these electrically charged electrons. By the way, I've drawn arrows on here for the particles, and arrows kind of go in the direction of time for normal particles. So a normal fermion, say the electron, we draw the arrow going forward in time to illustrate that. Antiparticles, though, will draw in the opposite direction, and we often put a bar over the label for the particle. So F bar is an antifermion, and the particle points in the opposite direction. And that's because in the relativistic theories for quantum mechanics, in the early days, we had funny negative energy states. And one way to think of those states were to think of as a normal particle moving backward in time to explain antimatter. So hence we kind of draw the arrow backwards. Now, what are Feynman diagrams really trying to represent? Well, they're actually, although I'm kind of showing them as a geometric scattering, graphically, they're actually representing mathematical terms in a perturbative expansion of a field theory calculation, where the terms are integrated over all space and time. So they're going to be leading order and higher order terms in this perturbation series. I'm drawing, say, the leading order term, but there would be higher order interactions that are have higher orders of the couplings. But you do integrate over all x and t. And so any time ordering, like I showed, like the first electron emitting a photon, then it's absorbed by the second electron, you shouldn't infer that. This is all happening within the uncertainty principle, localized in a small region of space. We can't infer which one emitted and which one absorbed. We integrate over all cases, whether the first one emitted or the second one emitted it, all right? So it's just illustrative, but don't take it too literally. All right, so let's see how we can use this graphical language to describe interactions in electromagnetism. As I said, for electron-electron scattering, we're just exchanging a photon between the two electrons. And here I've drawn it vertically to say, well, I don't know who's emitted it first because I can't know by quantum mechanics. But I could have also had an electron and an anti-electron, a positron, annihilate into energy. And so here I've drawn the electron coming in, the anti-electron coming in, but with the opposite arrow, and they annihilate at a point, and they become energy, but that energy takes the form of a photon, the propagator of the electromagnetic force. That photon propagates a very tiny distance within that uncertainty principle, and then can create two other particles. In this case, perhaps a muon and an anti-muon, a mu minus and a mu plus. And so we can have a mu minus and mu plus come out. Could have been another electron and positron, by the way, or even quarks and antiquarks. Just picking one example that happens electromagnetically. These were scatterings or reactions, if you like. We can also have decays. So we can also talk about the decay of a pi zero. It's a neutral pion. And when we talked about in the quark model, neutral pion can be thought of, for example, as a bound state of an up quark and an anti-up quark. Or it's actually a linear superposition, also the down quark and anti-down quark. But at any one instant, it might be an up and an anti-up quark, and that quark and anti-quark could annihilate. And so here we see the up and anti-up annihilate and become two photons in the decay. And you need the two photons to conserve momentum, if you may recall, when we talked about conservation laws. Those were electromagnetic interactions, drawn with my schematics for how to show the electromagnetic interaction propagated by a photon. Let's move on to weak interactions. So these are the interactions that describe beta decay. Let's start, for example, with the decay of a muon into an electron, and then we have to conserve lepton number for each species of lepton, a muon neutrino and an anti-electron neutrino. So here's how that goes. I have a muon coming in, and it's going to decay via the emission of a W minus boson, because it's got to carry that negative charge. Although I should be careful because, again, I can't infer time ordering. But let's just follow this as if it were going in this time. The W minus carries the electric charge off the muon, so now I have a neutral muon, which is known as a neutrino. So I have a muon type neutrino. That W minus can then couple to an electron and an anti-electron neutrino in the final state. And so that's how I'd represent this interaction. This would be the leading order diagram in that perturbation theories. And this is the beta decay of the muon into an electron plus two neutrinos, the muon type and the anti-electron type. What about what you're familiar with from nuclear physics, the decay of the neutron? The decay of the neutron goes to a proton plus an electron plus that anti-electron neutrino, which was up to Pauli to come up with the hypothesis that there was this then invisible particle necessary to conserve energy momentum. Well, in the quark parton model, we've learned that the neutron can be represented by an up quark and two down quarks. And the proton is two up quarks and a down quark. So at the quark level, what's happening is we're taking a down type quark in the neutron, we're emitting a W minus just like the muon did, and turning it into an up type quark. And then the W minus, just like it did in the muon decay, couples to an electron and an anti-electron neutrino. So this beta decay of a nucleon is happening at the quark level by changing one quark into another via the W boson emission. Now, one thing to note is the weak force is the only force that can change the type, aka flavor, of a fundamental particle. It can turn a muon into a muon neutrino, or a D-type quark into the up-type quark. The electromagnetic force, the strong nuclear force, they can't do that. Only the weak force can change fundamental particles into different ones. Interesting, right? Something special about the weak force. The other thing to note is that weak interactions, they are very, very short ranged. And that's mainly because the W and Z bosons have an enormous mass. So that heavy mass, which has for muon decay, doesn't have enough mass to create a real W boson in its decay. So it has to be a so-called virtual W. That means it's within the uncertainty principle. It can create a large delta E, provided delta T is short enough, so that the product is about H bar. And small delta T, even if the particles move at the speed of light, means a small distance. So it's very short range, these weak interactions, like a thousandth of the size of a nucleon. All right, finally, that brings us to the strong nuclear force, the strong interactions. So let me describe how those can take place. Let's do something maybe a bit complicated for hadron decays. Here's an anti-excited kaon, neutral kaon, a K0 star bar that can decay to a K minus and a pi plus. So a negatively charged kaon and a pi plus, positively charged pion. Well, the K0 star bar is a strange quark and an anti-down quark. Because this is an antiparticle, we have strangeness -1 here in this case, so that's the strange. What is happening is the strange quark here can be thought of as emitting a gluon, and that gluon can then turn itself into an up quark and an anti-up quark. So you created some energy, and then that energy takes its form of mass of an up quark and anti-up quark. Now, that gluon could have also been emitted off of the anti-down type quark leg here. So I'm taking the structure of the hadron term of the quarks and showing a particle interaction off of one of the quarks. And I could emit an anti-up and an up quark. Those combined, a strange quark and an anti-up quark makes the K minus, a negatively charged kaon, and the up and anti-down makes a positively charged pion. And so that's how that decay looks like at the quark level. But I can also have reactions, and I could have two quarks come in. Maybe they were in two protons that were colliding. They can exchange a gluon between them to scatter, just like electrons can scatter by exchanging a photon. Quarks can scatter by exchanging a gluon. They can also exchange a photon too, because quarks are electrically charged. But the strong nuclear force is much stronger, and so this dominates the scatterings. But I could also have a quark and antiquark annihilate. So here's a quark coming in, and antiquark, they meet, they annihilate into energy, which takes the form of a gluon, which can then create new matter. And for example, if I take the heaviest form of matter, a top quark, it can make a top quark and an anti-top quark. So I have two quarks, maybe light flavored quarks annihilate, say from an incoming two protons colliding. So I have the quark and antiquark collide. And I can create two heavy top quarks provided I have enough incident energy to create all that MC squared. And that's the diagram that came in for the discovery of the top quark. Okay, so this was just showing graphically how you can represent the quark level what these interactions are doing. And so maybe just to conclude, one more point. One more point to make about strong force is unlike the electromagnetic force, right? The electromagnetic force, Coulomb's law, you remember, falls off as 1 over r squared. 1 over r squared with 1 over distance squared, in other words. The strong force gets stronger with increasing separation. So it's kind of opposite. The farther apart you pull two strongly charged particles, the stronger the force between them. And the closer you bring them, the weaker it is. It's opposite the electromagnetic force between these color charged objects. So kind of strange in that way. If you pull them too far apart, there's a huge amount of energy it takes to do that. And in fact, what will happen is that energy will take the form of other particles that will pop out from pulling two quarks, say, far apart. But that's a whole other story. So, and then one other thing is, although it has this opposite behavior, the gluons themselves are massless like the photon. But unlike the photon, which is electrically neutral, the gluons have color charge themselves. So gluons interact with gluons. Photons don't directly couple to other photons because they have no electric charge, and the electromagnetic force couples to charge. But the gluons in the strong force have strong charge, so gluons themselves couple to themselves. So it's definitely a more complicated theory. Okay, so just to end, these diagrams we're showing, as I said, are known as Feynman diagrams, and obviously owing to Richard Feynman. And so this is actually a van he owned and drove his family around in 1975. And he had various Feynman diagrams written on or drawn on his van to represent these calculations in quantum field theory. And so this was at a time when it was displayed at the Fermi National Accelerator Laboratory. It had a little plaque there about Feynman having done that. And anyway, somewhat amusing. Okay, so that ends this lecture on particle interactions and their graphical representation in Feynman diagrams.